Okay, I'm going to get started. Wanted to start with just a reminder about the weekly cycle that we're going to go through. The lecture material that we introduce in, say, this week, the homework that will be due next Monday, the recitation worksheet that would normally be next Monday. So that's the weekly cycle. I just wondered if there's any questions on, now you've had a chance to think about it, how that works. Any problems with how that works? You want to check that you can get into WebAssign to complete your homework. And I think I checked that everybody, it looks like everybody was able to do the lecture quiz from the last class. So any questions on all that? Okay. Last class we talked about electrical attraction and repulsion, and we talked about positive and negative electrical charges as the origin source of electrical attraction and repulsion. And we talked about the electrical nature of matter, that matter is built out of electrical building blocks, electrons and protons. Today's class, we're going to move along and we're going to talk really specifically about two things. We're going to talk about Coulomb's law for the electrical force in today's class, and we're going to talk about the superposition principle of electrical forces in today's class. So those are the two big topics. We'll also work through some examples, illustrations of Coulomb's law, superposition principle of electrical force. Now, last class was, in a way, a little bit of a misrepresentation of what our classes will be like in 213. So in last class, I didn't have any equations. I didn't use any algebra. I didn't use any geometry. I didn't use any trigonometry. So most of our classes are going to involve some mathematics. It's algebra. It's a bit of geometry, it's a bit of trigonometry. And today's class we'll see some math, some algebra, some trig, and some geometry. So as we work through the math, if there's things that, if there was something that you don't understand, probably means that 90% of the class doesn't understand it. So make sure you ask me a question when it comes to not just the physics, but the math that we're using to work on the physics. Okay, so first half, Coulomb's law of electric force, then second half, superposition principle for electrical force, in both cases with some examples. So Coulomb was not really a scientist, he was more of an engineer. So he was an expert on things like forces on beams and strengths of materials, and that's kind of engineering. He was in construction, so he built bridges and canals and buildings. But his interest, his hobby, was actually how electricity works and how magnetism works. And he developed Coulomb's law for how electricity works. So he applied his skills in engineering to the problem of the electrical force between electrical charges. So he had unique experience in engineering that he could apply to experiments with electrical forces between electrical charges. Specifically, he constructed an instrument that we call a torsion balance. And here's a picture of the torsion balance. And I'll say a few words about torsion balance. But it's a device that allows you to accurately, precisely measure tiny forces, very, very small forces. And he wanted to measure the very, very small forces between electrical charges. He was able to map out the forces between electrical charges, and that's where Coulomb's law came from. So based on his engineering expertise, he was able to build a torsion balance. He was able to measure tiny forces between electrical charges, led to Coulomb's law. The way it works is that the torsion balance involves a long vertical fiber here. And in the use of the torsion balance, you twist the fiber. You turn the fiber. And that creates a kind of a restoring twist. As you twist the fiber due to some external force, like an electrical force, it tries to twist back. There's a sort of spring force turning back. And you can balance the applied force, say from an electrical charge, with the restoring force from the fiber itself to measure tiny forces. It's like you could use, a more familiar case would, you could use a spring to measure forces, right? If you hang a mass from a spring, the spring will stretch, and the spring will stretch until the spring force balances the weight of the mass, the gravitational force. And that's what's happening here. He's got an electrical force, no gravitational force. It's twisting the fiber, not stretching the fiber. But again, in this torsion balance, you measure the electrical force by balancing it against this kind of spring force of twisting the fiber. So that's how it all works. It was later used for a very famous experiment, not in the context of electricity, but in the context of gravity. It was used in the context of gravity. You might have met it in 2011 by a famous scientist, Henry Cavendish, who was able to, instead of measuring electrical forces between objects with the torsion balance, he measured gravitational forces between objects with the torsion balance, and that now enabled him to determine the weight of the Earth. So it's a very, very, very famous, very, very, very important experiment at that moment that the Earth was weighed. And it was done with a torsion balance that was invented here, that Coulomb invented. Okay, enough of that. So with his torsion balance, Coulomb was able to figure out a number of features of the electrical force. And so this is the list of the results of his torsion balance experiments. And I'll just go through them and then we'll put them all together. So first one is that the force between electrical charges varies with the distance, the separation of the electrical charges, and it actually falls off with the distance, and it falls off as the square of the distance. We call that inverse square law. So that's a very important feature of the electrical force between electrical charges. Actually, last class we realized that the electrical force must fall off with distance, because that's why charged objects attract neutral objects. But Coulomb figured out exactly how it falls off with distance. It falls off as the inverse square of the distance, what we would call a 1 over r squared law. So that's a very important point. The force between two charges, that depends on the amounts of the two charges. In fact, it depends on the product of the two charges. So if you make one bigger, then you'll increase the force. If you make the other one bigger, you'll increase the force. If you make both of them bigger, you'll increase the force even more. So it's the product of the two charges, I call them Q1 and Q2 here, that determines the strength of the force. I put the little braces, vertical lines on either side, because in terms of the strength of the force, it doesn't really matter whether it's positive or negative charges. What counts is the size of the magnitude of the electrical charge, and so it's the size. That's what the braces mean. That's what the vertical lines mean. It's the size of the electrical charges that count. The force, next point. The force is along an imaginary line that joins the two charges. So imagine I've got a charge in the left hand, right hand. Imagine a line, an imaginary line between those two charges. The force acts along that line. Now, if the charges are opposite charges, so one's plus and one's minus, then it's a force of attraction. So it's along the line towards the other charge. If the charges are like charges, so that might be two positive charges or two negative charges, then it's a repulsive force. So again, it's along the line, but away from the other charge. Because there's two, imagine a line between the two charges. There's two directions along that line. There's one towards the other charge, there's one away from the other charge, and one corresponds to attraction and one corresponds to repulsion. So these are all the ingredients in Coulomb's law that Coulomb mapped out with his torsion ballast. So it was a great achievement that Coulomb was able to build this instrument. Coulomb was to map out the working of the electrical force, the size and the direction of the electrical force as a function of the amounts of charge, as a function of the distance between the charges, and so on and so forth. So he put it all together in one succinct law. And that's described on this slide here. So in this slide here, I got two sketches. There's one on the left that corresponds to like charges. So if you look here, this is a positive charge and this is a positive charge. They're like charges. It could be two negative charges also. And then there's another sketch on the right for the other situation when it's unlike charges. So here we've got a positive charge downstairs and we've got a negative charge upstairs. So the sketches are showing us these two situations of attraction and repulsion. The sketches indicate a few important things in terms of writing down Coulomb's law and expressing Coulomb's law. So they label the amount of charge, so Q1 and Q2, the quantities of charge that we're bringing close to one another. There's the separation between the charges. So we're going to call that R. We typically call that R. Here's the separation between the two positive charges. Actually, the separation between the two negative, the positive and negative, isn't marked on this sketch, but it would run from here to here. That would be that separation. So it's a bigger separation on this right-hand plot. So that's R. And then finally, we also see the imaginary line between the two charges. That's the dashed line. That's the dashed line here. But we also see the force vectors that the two charges are experiencing. So look, the blue arrows on the left-hand side are the repulsive forces that the two charges experience due to their neighbor. The blue arrows on the right-hand side are the attractive forces that the two charges experience due to their neighbor. And so these pictures define all the important quantities in determining the size and direction of the forces in terms of the separation of the charges, the amounts of the charges, so on. This below, this big equation, is Coulomb's law. So this says that the magnitude of the force between the two charges, it could be the picture on the left or the picture on the right, is equal to, it's the product of the charges. We talked about that. So here's Q1 times Q2. I'm really thinking about the sizes here, so hence the braces. And then divided by the inverse square of the distance. That's downstairs here in the denominator. One more thing that's just appeared is a constant. This constant K is a constant that kind of determines or characterizes the strength of electricity. If you made that number bigger, electricity would be a bigger force. If you made it smaller, electricity would be a smaller force. So this is a constant of nature that is determining the overall strength of electrical force. We give it the symbol K normally. We call it the Coulomb constant normally. And so this is the strength of the force. Now, importantly, you've got two charges interacting. Charge on the left will experience a force due to charge on the right. Charge on the right will experience a force due to the charge on the left. So there's two forces here. Those two forces are equal in size, magnitude, they're opposite in direction. That's Newton's third law, actually, that forces always come in pairs. When something interacts with something else, there's always a pair of forces. And here's an illustration of that. These electrical forces come in pairs. There's two forces on the two charges, and they're equal sized in their opposite directions. So you see that in the figure here. This force is down and to the left on the left-hand charge. This force is up and to the right on the right-hand charge. They're equal and opposite forces. And likewise over here, these two forces are equal and opposite forces on the left-hand lower charge, the right-hand upper charge. So that's Coulomb's law. Oh, sorry. I should say one thing about this. So that's a big breakthrough in writing down a law between 2-point charges. But it is a very special case. It's just a law for the interaction of two-point charges. It doesn't say anything about what's going to happen if we got more than 2 charges, 3 charges, 4 charges, so on and so forth. So it's a very special case, the simplest case of the interaction between 2-point charges. I should also say that when I say it's the interaction between 2-point charges, really by the word point, because nothing is truly a point, I mean that the size of those charges, maybe they're on little spheres, the size of those spheres is small compared to the distance between the charges, so that they kind of look like points. Kind of like, you know, if you look at the solar system overall, then, you know, Earth, Mars, Venus, the Sun, they kind of look like points. They're not points, but on the scale of the solar system, they do look like points. And that's what Coulomb's law applies to. When the separation between the charges is much bigger than the size of the charges. Okay. So let's look at a couple of examples. I've got a couple of examples of Coulomb's law here. I think one I'm just going to show you on the slides, and then the other one I'll work on the document camera just to work out the second problem. Okay, so here's the first problem. Now you've just met electrical forces. The previous semester, or previous time you took 211, you met gravitational forces. Let's just compare the characteristics, strengths of gravitational and electrical forces. Now, you might say, okay, let's do that. Let's compare the strength of the force between two 1 kilogram objects, that's a gravitational force, so we can figure that out, and the strength of the force between two 1 Coulomb objects. That would be an electrical force. So we could compare that. But it's really not a very natural comparison. You see, the humans made the units of kilograms that we measure mass in. Humans made the units of coulombs that we measure charge in. So it would be rather unnatural or artificial to compare the forces, electrical gravitational forces, between a pair of Coulomb charges or a pair of kilogram masses. There's a better, more natural comparison we can do. And the most obvious, most natural comparison that we could do is use nature's building blocks, you know, electrons and protons. And specifically, we're going to compare the electrical and gravitational forces between the electron and the proton in the hydrogen atom. So the electron and the proton in the hydrogen atom have electrical charge, so there's an electrical force there. The electron and the proton in the hydrogen atom have mass, so there's a gravitational force there. Let's just compare those two forces in that hydrogen atom situation. So that's all I'm going to do. On this slide, I just wrote down the numbers we're going to need. What numbers will we need? Well, look, here's the picture of the problem that we're going to figure out. On the left-hand side, this is a negatively charged electron, the blue blob. On the right-hand side, the orange blob is the positively charged proton. And here R is that separation between the two charges and between the two masses. To calculate the gravitational force and the electrical force, we need a number of quantities. So we obviously need to know that for the electrical force, the charges of the electron and the proton. So here I wrote that down. Negative 1.6 times 10 to the minus 19 coulombs, positive 1.6 times 10 to the minus 19 coulombs for the electron and proton. So we need that to figure out the electrical force. We also need to know the masses of the electron and the proton. So I wrote that down here. Remember that the electron is that tiny light object that buzzes around, and its mass is about 10 to the minus 30 kilograms. I wrote down the number here. The proton is much heavier, and its mass is, about 1.7 times 10 to the minus 27 kilograms. So I wrote that down here. So these numbers I need to figure out the gravitational force between the two objects. I also need to know those constants of nature associated with electrical force, associated with gravitational force, that determine the overall strength of electrical and gravitational forces. So I wrote those down upstairs here. This is Newton's constant for gravity. It determines the strength of gravity. This is the Coulomb constant for electricity. It determines the strength of electricity. And so we're gonna need those two numbers too. You'll notice, right, these units are man-made units. These units are man-made units. They involve newtons and meters and kilograms and coulombs. But in our man-made units or human-made units, the gravitational constant is a very small number. It's some large negative power, 10 to the minus 11. The Coulomb constant is a large positive number. It's 10 to the power 9. Okay, so let's figure out what the relative sizes of gravity and electricity are in the hydrogen atom. So we need Coulomb's law. That's this equation here, just written it down again. We need Newton's law of gravity. That's this equation here, just also written it down. So this is from 211, this is now 213, and we want to compare these two forces. So how do we compare two numbers? How do we compare two strengths? We would take the ratio of the two. If I divide the electrical force strength by the gravitational force strength, that's going to tell me, whether electricity is stronger or gravity is stronger. And the number will tell me how many times electricity is stronger than gravity. And so I want to calculate the ratio of these two forces given by these two equations here. And so I want to calculate the ratio, and so I just fed in the equations. This is Coulomb's law in the numerator. This is Newton's law for gravity in the denominator. Now, you see an interesting, useful thing here. Both of them are 1 over r squared laws. So both of them are inverse square laws. And so the inverse square in Coulomb's law and Newton's law cancels out when I'm comparing the strengths of the forces. I don't need to know how far apart the electron and the proton are in the hydrogen atom. And I didn't write it down in the last slide. I just called it r, because it's going to cancel out. Because both forces, interestingly, work the same way. They're both 1 over r squared laws. Okay, so we'll cancel that out. And all I've got to do is calculate this quantity here. And if you look at this quantity here, it's the ratio of the constants for the forces times the ratio of the product of the charges divided by the product of the masses. These are the 6 numbers I wrote down on the last slide. So we can just plug in those 6 numbers. I didn't write that all out. I couldn't face that task. But I did do it on the calculator. And if you plug in the charges, so remember the charge is about 10 to the minus 19 coulombs. So there's a very small number in coulombs, but the masses are even smaller. The masses are like 10 to the minus 27, 10 to the minus 31 kilograms. So they're even smaller in terms of powers of 10. Also, the Coulomb constant was a big positive power of 10. The gravitational constant was a large negative power of 10. So K is big and G is big. All those factors to conspire to make this ratio an enormously large number. It's actually about 10 to the 40. Gravity is 10 to the, electricity is 10 to the 40 times bigger for the hydrogen atom than the gravitational force. It gives us a scale of, in nature, how much bigger electricity is than gravity. In nature, electricity is an absolutely huge force, massive force. By comparison, gravity is this tiny, 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 feeble force. It raises an interesting question, which is, if electricity is so strong and gravity is so weak, by this massive factor of 10 to the 40, why do we ever notice gravity at all? Why don't we just, only see electricity? The reason why we do notice gravity, right, with glued to the Earth, stuck to the Earth by gravity, the reason that we do notice gravity is that there's another feature of gravity that distinguishes gravity from electricity. In fact, that gravity is always attractive. Electricity can be attractive or repulsive. So think about the Earth. So imagine now the Earth. Imagine all the electrons and protons that make up the Earth. Imagine all the electrically charged components that make up the Earth, the negatively charged electrons, the positively charged protons. Imagine all those electrons and protons interacting with, imagine yourself, imagine your own body filled up also with electrons and protons. Negative electrons, positive protons. So for gravity, every electron and proton in the Earth will attract every electron and proton in you, and it's always attractive. So gravity kind of builds up and up and up as we consider each electron and proton pair in the Earth and in you interacting together. It's always attractive. It's always accumulating. Electricity, on the other hand, well, you've got electrons and protons in you, you've got electrons and protons in the Earth. Sometimes, if it's an electron and an electron, that'll be repulsive. Sometimes, if it's an electron and a proton in you and the Earth, that will be attractive. When you add up all the electrical forces between all the individual electrons and protons in the Earth and in you, there's lots and lots and lots of cancellation. There's lots of electrical forces that are attractive, electrical forces that are repulsive. Overall, because you're neutral and the Earth is neutral, there's no net electrical force. The electrical force was 10 to the power 40 times stronger, but you notice the gravitational force between you and the Earth. And so that's why much, 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 much weaker gravitational force overwhelms the much, 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 much stronger electrical force when we think of objects like the Earth and us interacting with the Earth. Okay. Second problem. So in this problem, we're asked to think about this situation pictured here. So in this situation, and it's actually this situation here, I've got two little spheres, and they're hanging from two strings. And what I've done, normally they would just hang vertically under the influence of gravity. What I've done is I've charged them up, equally charged them up. so that not only do they hang under gravity, but now they interact with one another electrically. And because I charge them equally with the same amounts of charge, I've called it Q in the picture, they'll repel one another. And so the one on the left is pushed towards the left, away from the one on the right, and the one on the right is pushed away towards the right, away from the one on the left. And so that's this situation that's pictured here. Just to break things up a little bit, I'll show you, I did this. I did this little test because, you know what, I was a little bit jealous of Coulomb. Coulomb invented a torsion balance. He measured electrical forces between electrical charges, and he got Coulomb's law. Because I had a good idea that I could not invent the torsion balance, he's already done that, but I could invent another way of measuring electrical forces between electrical charges, not by the twist of a wire, where you're really comparing electrical forces with the force exerted by the wire, twisting the wire. I could do it by comparing electrical forces with gravity. And that's what this experiment does. It compares electrical forces with gravity. So here's my arrangement. Guess I could make this bigger, couldn't I? And I'm charging up a piece of plastic pipe. And we're charging it up with a piece of cat's fur. And I'm going to bring it up to those two little spheres, and I touch them. And charge jumps onto those spheres, and you saw them blast apart why did they blast apart? Due to electrical forces. And then gradually they come to an equilibrium. They were originally hanging vertically downwards, touching one another, but now they're hanging vertically downwards, but also pushing away from one another because they're repelled from one another. And that's exactly the situation that I recreated here. And what I'm going to do is, based on the angle that they hang at an angle of 2 degrees away from the vertical, I'm going to figure out the amount of charge that I placed on both of those objects to create a repulsive electrical force that makes them hang at 2 degrees. So this is a way I can measure the charge on the little spheres determine the charge on the spheres by measuring the angle that they hang at 2 degrees. Okay, so let's go ahead and do this. Let me just show you this figure one more time, and then I'll go to the document camera if I'm capable. It's somewhat doubtful. On the figure, I've labeled the length of the string. So they're 40 centimeter strings. I labeled the angle that the two charges hang at 2 degrees from the vertical. I measured their mass. It's 5 grams. And so I've labeled that too. There's one little thing I've added to the figure. So this is like, if you would go for a run, which I wouldn't do, you might warm up before that. You might stretch. So this is kind of the physics equivalent of that. I've got to solve this problem of the charges. What are the charges? A little warm-up exercise, because I know I'm going to need this, is I'm going to calculate this distance here, this horizontal separation between the two charges, because that's important in Coulomb's law. That's a little bit of trigonometry and a little bit of geometry. I've constructed on my figure a right-angled triangle. There's one on the left and there's one on the right, actually. The hypotenuse is the length of the string, 40 centimeters. The angle upstairs here is 2 degrees. I want this distance here, the separation of the charges. It's this distance on the left between the left-hand charge and the center, plus this distance on the right between the right-hand charge and the center, So it's 2 times this side, opposite side of the triangle. And the opposite side of the triangle is L sine theta. It's 0.4 meters times sine 2 degrees. And so I did this little geometry calculation, trigonometry calculation. There's 2.8 centimeters between the 2 charges. And we kind of saw that in the movie. Okay. So I'm going to go ahead and solve this problem. Wish me luck. Here's the arrangement. And you notice I've added the 0.028 meters. That's the separation between the charges. I've also got the length of the string. It was 0.4 meters and the angle's 2 degrees. In solving this problem, you can focus on either the left-hand or the right-hand charge. Either is perfectly fine. I focused on the left-hand charge. And the first thing I did was to go about sketching the forces that are acting on that left-hand charge. I wanted to make sure I understood all the forces that are involved in this problem. So let me start by doing that. One force is gravity. So it's downwards. I gave it a downwards arrow, and I've indicated with, if you can't read that, that is my F with a subscript G. That's the gravitational force. There's an electrical force that's acting. Just a repulsive electrical force between the 2 charges. So for the left-hand charge, it's going towards the left, and I'll just indicate that as Fe. That's the electrical force. Is that it? That's not it. There's another force. That's the tension force in the string. And so I've got to add the tension force in the string. That acts along the string. So here's the tension force, a third arrow. I'll just call that T. It is a vector too. It has a direction and it has a size. And it's neither horizontal or vertical. It's acting at an angle, actually acting at 2 degrees to the vertical. There's an important point here. The tension force has a vertical component and has a horizontal component. I won't write them down because I'll make the diagram too complicated. But this vertical component here, that would be T cosine 2 degrees. And it's mostly in the vertical direction, the tension. This little piece here, this would be T sine 2 degrees. So there's a little bit of horizontal component. Okay. We'll see later on that when I drew these 3 forces, I didn't really carefully draw the sizes of the forces. We're going to work that out. Because actually, this electrical force, I wanted to show it as kind of big, but it is smaller. It is smaller than that, but we're going to see that in a moment. Okay, so now we've drawn the forces. I want to write down the important principle that allows us to solve this problem. And here it is. This is the principle of equilibrium. So those 2 forces hanging on those 2 strings are just sitting there in space. They're not flying around. They're at rest, staying at rest, which means that they're in equilibrium, which means that the sum of the forces acting on them is 0. So this sigma here is sum. This is sum of forces is 0. I'm going to be thinking about the left-hand charge, but it applies to the right-hand charge too. Let me expand this equation a little bit. So it means actually that the electrical force, the electrical force Fe plus the gravitational force Fg plus it's going to drive me mad, tension force T, those 3 forces, which are vectors, I'm careful to indicate they're vectors, they have directions and they have sizes. add up to 0. So that's the key to solving this problem. That's what's going on here. If you could, special glasses, you could see the forces. That's what you would be seeing in this problem here. Now, it's handy if we break that equilibrium of the forces out into the equilibrium of the forces in the horizontal direction, the equilibrium of the forces in the vertical direction. So we're going to do that. When there's an equilibrium of forces, it means in the horizontal direction, the forces cancel. In the vertical direction, also, the forces cancel. And that's going to be sort of helpful for the actual practical problem solving we're going to do. So let me write that out too. Now there's going to be two equations, and I'm not going to indicate the quantities of vectors, because now it's just components of vectors. I'll write them down first. Okay. Two equations here. This equation here is about equilibrium in the vertical direction. And it's just saying that the downwards gravitational force, Fg, is counteracted by a component, the vertical component of the tension force. And the vertical component of the tension force is T cosine theta. So there's two forces acting vertically, tension as a vertical component, and gravity acts all vertically, and they're equal and opposite. And so the gravitational force downwards is balanced by T cosine theta, the piece of tension that's upwards. This is positive, Fg, this is negative, T sine cosine theta, because they're in opposite directions, because they're balancing one another. The same thing applies, same idea applies to this second equation. So in this second equation, there's a second balance happening. It's in the horizontal direction. This electrical force towards the left is being balanced by the horizontal component of tension towards the right. So here's the electrical force towards the left. Negative direction is towards the left here. Then there's a positive tension component towards the right, and that's obtained by T sine theta, or T sine 2 degrees. So this is really just elaborating on that equilibrium between three forces, elaborating on it in a way that I write down the equilibriums that are going on horizontally and vertically. And that enables us to solve this problem. So now I'm going to solve the problem. I'm going to find what the charges are, but that really involves finding what the electrical force is first. So what you're going to see now is me first working out the electrical force. I'm going to figure it out by working out the gravitational force, by working out the tension force, then the electrical force, and then we'll find out what the charges are. That's easy. Okay, gravitational force. What's the gravitational force in this situation? Well, that's just mg. We know that. The mass of the sphere was 5 grams, so it's 0.00 kilograms, times the acceleration of gravity. That's 9.8 meters per second squared. If you calculate that, you get 0.049 newtons. So that's gravity. We've now nailed down one of these three forces. Next one I'm going to calculate is tension. Tension. Tension equals force of gravity divided by cosine theta. Can you see where that came from? That came from this equilibrium here. The force of gravity is balanced by T cosine theta. If I rearrange that equation here for the vertical equilibrium, I get this second equation here. I know the gravitational force, so now I can figure out the tension force. If you plug in the numbers, actually, to the number of digits I'm writing things down, it's also 0.049 newtons. It's actually, in the next digit, slightly smaller than that. It's because the angle was so small, T cosine theta is really close to T itself. So now we know the tension force is just fractionally less than 0.049 newtons. We want the electrical force. To find the electrical force, now I know both gravity and the tension force. Well, I can just use the second of the equilibrium equations, this one here. If I rearrange that, it tells me that the electrical force is just T sine theta. And again, now just got to multiply 0.049 newtons by the sine of 2 degrees. The sine of 2 degrees is a very small number. So we end up with 0.0017 newtons. That's the size of the electrical force. So that was a little bit of working out, understanding the equilibrium of the forces, understanding what forces are present to solve for all the individual forces. Most importantly, our target was solving for the electrical force, and we now know it. It's towards the left, and it's 0.0017 newtons in strength. Now it's easy to find, so the last step, I'm going to find the charge on the two spheres from Coulomb's law. Coulomb's law says that the force between the two charges is the Coulomb constant K times the product of the charges, so that'd be Q squared here, divided by the square of the distance between them. That's R squared here. If you look at that equation, the only number in that equation that you don't know is Q. It is the charge. That's the quantity we want to figure out. And so I'm going to rearrange this equation. I'm going to rearrange it for Q. That means I'm going to have to, what am I going to have to do that? I'm going to divide through by K. I'm going to multiply through by R squared. The end result of rearranging this I won't bring these pencils again. Is this little, not this little equation. Is this little equation here. Since nobody can read it, this says that the charge equals the separation between the charges times the square root of the electrical force divided by the Coulomb constant. It's just rearranging Coulomb's law. Every number on the right-hand side I know. On the right-hand side is R, the separation. On the right-hand side is Fe, the electrical force. And on the right-hand side is the Coulomb constant. So I know all those numbers. I can plug them all in. I'm not going to write it down. We'd be here to the end of the class if I was going to do that. I plugged them all in, and that told me that the charge is 12.2 nanocoulombs, 10 to the minus 9 coulombs. That's the charge on either charge. Look, I just invented, rather than the torsion balance, another type of balance in which I could measure the charges that correspond to electrical forces. And that's what Coulomb was able to do. He measured the relationship between electrical charges and electrical forces. And I did it by balancing gravity with electricity. Coulomb did it with balancing electricity versus a twisting force. Yeah.
Should all the forces equal 0?
The sum of all the forces adds up to 0, yeah.
Well, but they're all positive.
To add them up, so that's a good question. The forces are vectors. So they have magnitudes, they have directions. So you can't say, to add them all up, you can't say, well, look, it'd be 0.049 plus 0.049 plus 0.0017. That's adding up numbers. And these forces have directions. So one's to the left, one's downwards, one's up and towards the right. You have to add them up as vectors. if you add these 3 strength forces up in the directions on the picture, they do add up to 0. So it's a very important point. And that was the whole way we had to solve the problem. So it is, what you're stressing is the forces are vectors, and you have to be very careful when you add them up. You have to add them up as vectors. And I'll show you the second example we're doing in class will be exactly that problem, adding forces up as vectors. So yeah, they would add up to 0 if you properly accounted for the directions of them. Any other questions on that? Yeah.
Where did you get the value for the constant?
The Coulomb constant? So, I mean, Coulomb got it from his measurements. And it's it's just no. It's 9 times 10 to the 9 newtons meters squared per Coulomb squared. It's actually measured much more precisely than that. So it's actually 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So it is a fundamental constant of nature that is measured. There's nobody that can calculate it. You can't calculate it. You can only measure it, observe it. So that's a good point too. Okay, I've forgotten what I'm doing. Superposition principle. This is the second topic. We said that Coulomb's law applies to the situation where you get 2-point charges. You can add up, you can calculate the force between 2-point charges, but that's a very special situation. And actually, most situations you meet don't involve just 2-point charges. So Coulomb's law alone is not that useful. You have to supplement Coulomb's law with another law or principle. It's called the superposition principle. And this overhead describes the superposition principle. But let's see, I've got to take it off this camera. In this figure here, we're imagining a more complicated situation. I got one charge here, charge number 1 in teal, or whatever this color is. I got a second charge here, call it number 2, in lime green, or whatever this color is. And I got a third charge here, in orange. And these 3 charges are interacting with one another. So this is beyond Coulomb's law. Now I'm going to focus on charge number 1 and ask the question, what is the force on charge number 1? Well, there's a force due to charge number 2, and there's also a force due to charge number 3. The force due to charge number 2 I've indicated with this lime green arrow here. I don't know what the color is, not lime green, but green arrow here. It must be that these are opposite charges because it's an attractive force. So this arrow represents one of the charge's forces, second one. And then this orange arrow here, this is the force of the second charge. So this force due to charge number 3, that must be a like charge because this is a repulsive force. So these are the 2 individual forces, and you could get these 2 forces with Coulomb's law. How do they combine together? How do they superimpose together? That's what superposition principle is about. Superposition principle says that the resulting force, the total force on charge number 1, is the vector sum of the force due to this individual charge, which is this arrow on the left here, plus the force due to this individual charge here, this charge here, which is the arrow on the right here. You have to add up these 2 force arrows, and if you add them up, here's the resulting force, and that's the superposition principle. Here's a picture of the superposition principle. Here's an equation describing the superposition principle. The total force on charge number 1 is the vector sum of the individual forces on charge number 1 due to charge number 2 and due to charge number 3. So that's superposition principle. Look, in today's class, I'm just telling you this. And it's an observation that this is correct. In the next class, next week, we'll get a notion or an explanation of why superposition works. But for now, I'm just telling you that you can add up the forces of the individual charges to get the total force on the charge that you're thinking about. If you want to picture this, gosh, I lost my thing for changing the slide. Here it is. Here's a picture of the sum of the forces. Here I started with the force due to the second charge. That's this arrow here. And you know how on a picture you add forces. If I'm going to add a second force, I'm going to start it at the tip of the first force, draw it from there, and then the resulting force runs from the tail of the first force to the tip of the second force. So this is a picture of how you add these forces up. You can do it the other way around. I could have drawn the force due to charge number 3 first. Here's the force due to charge number 3, the orange arrow. If I want to show the addition of the other forces, the second charge's force, I would start it at the tip of the first force, and then and draw it, and then the resulting force would run from the tail of the force due to charge 3 to the tip of the force due to charge 2. So it's the second way that you could draw the superposition. But whether you do it this way round, or this way round, the resulting force is the same. Like if I add 1 to 2, I'm going to get 3. If I add 2 to 1, I'm also going to get 3. The same thing with vectors. If you add vector 1 to vector 2, you're going to get a resultant. But if you added vector 2 to vector 1, you also get the same resultant. So you can do the order in whatever order you like. Okay, where am I going? I'm going home. Quiz time. Okay, here's a quiz. Let me publish it. I'll give you a few minutes to think about it. Again, this quiz, you can talk amongst yourselves, discuss amongst yourselves, argue it out amongst yourselves. This quiz, like the Tuesday quiz, is not for credit. Next week, we're really going to start these quizzes for credit. In this quiz question, we're told we got these two charges, Q1 and Q2, that lie on this horizontal line. These two charges and a third charge that we're going to bring up have the same sign. So they might be all positive or they might be all negative. If we want the force of charge number 1 and the force of charge number 2 on charge number 3, so kind of exactly the situation that was pictured in the last slide or two, if we want the forces from these two individual charges on the third charge to add up to 0, to cancel out, do I put that charge, the third charge, here in region A? Do I put it here in region C? Do I put it in here in region B? Or is it impossible? Is it impossible to cancel out these electric forces? Okay, let me give you the answer. So for the two forces due to Q1 and Q2 to cancel out, how can those forces cancel out? Again, this is an example of addition of vectors, because we're going to add two force vectors together and the result has got to be no force. Meaning I couldn't add two numbers like 2 and 3 together to make 0, but you can add two forces that are vectors together to make 0. What you do is you add them together where they have the same magnitude, same size, but they have the opposite direction. Then they cancel one another out. So supposing my right arm is one force vector, my left arm is a second force vector. If I add them together in opposite direction, picturing the addition as going from here to here and then back to here, those two force vectors add to 0. And so we know first thing is that we've got to understand if the forces add up to 0, they must be cancelling one another out. If they're cancelling one another out, they must be in equal magnitude, opposite direction. Where in that picture could the two forces be in opposite direction? Remember, all the charges are either positive or all the charges are either negative. If you're over on the left, so I'm going to imagine, when I describe this, I'm going to imagine all the charges are positive, but we could have, the same argument would apply with all the charges being negative. But let's take all of them being positive. If we're over here on the left, then we're on the left of both of these charges. And so the forces, the repulsive forces, will be to the left. And so they can't cancel out because they're in the same direction. If we're over here on the right, all the forces are towards the right because we're on the right-hand side of the two charges. They can't cancel out here. But in between, there's some magic place where, because we're on the right of the left-hand charge, there's a force towards the right. We're on the left of the right-hand charge, which makes a force towards the left. The two oppositely directed forces can cancel out in this region here. So region B is the correct answer. Okay. I got to get moving here. I mean, I'm not leaving. I've got to get moving with the class. I wanted to finish up with an example, quantitative example of superposition. Here's an interesting question. Matter, we learned last class, is made of charges, electrical charges, equal amounts of positive and negative electrical charges that exert attractions and repulsions on each other. If these charges are exerting attractions and repulsions on each other, why does anything ever stick together? Why doesn't it all cancel out and everything, including us, fall apart? As an example of why things don't fall apart, let's think about why a sodium chloride crystal doesn't fall apart. This is a picture of a sodium chloride crystal. It's made up of smaller sodium ions, positive, and larger chlorine ions, negative. Why doesn't that arrangement fall apart? Let's see if we can compute why it doesn't fall apart. Why? This is part of a bigger question. Why is the whole of matter stable? Why are you stable? Why am I stable? Why is all the furniture stable? Why is everything not just falling apart under the equal amounts of attraction and repulsion from electrical forces? Interesting question. Obviously, it is stable. Okay, rather than calculate the forces in a massive sodium chloride crystal, let's take a nanocrystal. It's much more manageable. So I manufactured this nanocrystal here. So it has two positive sodium ions, two negative chlorine ions at the four corners of the crystal. So here in purple or whatever it is, magenta, are the sodium ions, plus Q, and here are the chlorine ions, minus Q and minus Q, arranged on a rectangle where the sides of the rectangle is just labeled A. It's just a symbol. And actually I'm going to calculate my answer in terms of not a number, but in terms of this symbol A and this charge Q. I mark the sides of the rectangle. What we're going to focus on is what is the force on this top left sodium ion, this positive sodium ion here. The distance A is important because that's the distance to the nearest neighbors, the chlorine ions. But this distance here, the diagonal, is also important. That's the distance to the other sodium ion, and by geometry, that's the square root of 2 times A. And so that's the important geometry. And we want to calculate the force on this guy upstairs here. So how did I go about doing this? The first thing I did was draw the forces, sketch the forces, because that's going to help me think about things. And then I went on to actually calculate the forces, compute the forces. So let's start with a sketch. This charge up here experiences 3 forces. One from the charge below, that's attractive. One from the charge from the right, that's attractive. One from the charge opposite, that's a repulsive force. So we got like charges below, like charges to the right, and downstairs here, opposite here, we've got a positive charge making a repulsive force. I drew those 3 forces. This green downwards force, attractive force, this green to the right force, an attractive force, this magenta force along the diagonal, that's a repulsive force. I labeled them F1, F2, and F3. So that's the force due to charge 1 over here, charge 2 down here, charge 3 in this bottom corner here. So those are the 3 forces, F1, F2, F3. I pictured their directions. I'm also imagining their sizes. Look, all the charges have the same magnitude. They have different signs, but this charge down here is further away, so I drew this force here. I drew it as smaller. So I did note that. To help me do the calculation of what the total force is due to the individual forces, to do this calculation here, we're going to try and find the resulting force by summing these 3 forces. I defined a helper. I needed a helper. A helper in this sense is just a symbol I'm going to use as an abbreviation for a combination of symbols that comes up time and time again. As I work through the 3 forces and summing up the 3 forces, I'm going to keep meeting this product here. This is the product of the charges divided by A squared, the separation between the nearest charges, times the Coulomb constant. That's going to come up time and time and time again. I don't want to keep writing that down. KQ squared over A squared, KQ squared over A squared. So I just called it F with no subscript. And that's just a symbol representing that combination. Using that symbol, the strength of the force due to the charge on the right is just F. The strength of the force due to the charge below is just F. The strength of the force due to the opposite charge is half F. It's square root of 2 as far away, but it's an inverse square law, so it's actually 2 times weaker. And so F is very, very handy to use here. I can write all the forces' strengths in terms of F in a very simple way. And just remembering it's just a shorthand for KQ squared over R squared. A squared. Okay, first step in adding the forces is this step here. So the new stuff on this slide here is this stuff below here. When I'm adding the forces, the way I'm going to add the forces is to break the forces up into x and y components, horizontal, vertical components. Figure out each forces, F1, F2, F3's horizontal and vertical components. That's the first step. That's on this slide. Next slide, we'll then add those components up to get the resulting force, the net force. That'll be on the next slide. This is just about finding the components of the three forces. I've defined my coordinate system. It's a normal one where positive x direction is horizontal towards the right, positive y direction is upwards. I labeled it here. What are the components of the horizontal and vertical components of F1? Well, I labeled them F1x, F1y, horizontal component, vertical component. If you look at the picture, the force is just towards the right. And so it has a horizontal component, that strength is F. It has no vertical component. That's easy. Similar thing for the horizontal and vertical components of force F2. It's just down. It has no horizontal component, that's 0, that's easy. It has a vertical component that's down in the negative direction, so it's minus F. So F1 and F2 are very simple to write down in x and y components because they're just either horizontal and vertical. F3 is a little bit more complicated. So if you look at F3, it's at an angle of 45 degrees to the horizontal, also 45 degrees to the vertical. So I have to multiply the strength of the force, that's the hypotenuse, by either a cosine of 45 degrees or a sine of 45 degrees to pick out the x and y components. So cosine of 45 degrees will give me the horizontal here, because the horizontal is the adjacent to this angle. Sine of 40 degrees will give me the vertical, because it's opposite this angle. I put in some pluses and minuses by hand. So this minus I put in by hand. This plus I put in by hand. I looked at the picture. It's in the negative x direction, so I put negative x direction. It's in the positive y direction, so I put the positive y direction. And so now I've got the three components of the three forces. Once you've got the three forces in component form, it's easy to add them up. To get the resulting force, so I called that, look, this is F subscript Rx. That's the x component of the resulting force. This is F subscript Ry. This is the y component of the resulting force. To get the resulting forces, I just have to add up for the x component, the three individual x components, for the y component, the three individual y components. This is just simple addition. So this is where I'm treating the vectors properly. Once you get it in x and y component language, you can add them just like numbers. Be careful of the sign, but you can add them just like numbers. And so here are the values of the three forces in the x direction. Remember, one of them had no component. F2 was just vertical. Here are the three components in the y direction. Remember, one of them also had no y component. It was F1. It was just horizontal. If I add them all up, I get these two x and y components here. That's the resulting force. We've solved the problem. Now, generally, when we think about the resulting force, we might want it not in x and y component form. We want it in the language of magnitude and direction. That's where I use Pythagoras' theorem. That's where I use inverse tangent. With Pythagoras' theorem and inverse tangent, I can find the magnitude, I can find the direction. So here's Pythagoras' theorem. The resulting force strength is just the square root of the sum of the squares as its x and y components. And that comes out to be 0.92 F, or 0.92 times kq squared over a squared. This should be an a squared. Sorry. This is just a proxy. So F was just a proxy for kq squared over a squared. And here's the angle. Here's the angle of the force. It's just the inverse tangent of the ratio of its y component to its x component. I plug in those numbers. Actually, inverse tangent gives you two numbers for two opposite directions. You've got to use the diagram to pick out the correct one. It's minus 45 degrees. It's just below the horizontal axis. That force is, what we discovered is that force is attractive. That charge is being pulled towards the center of the crystal because it's closer to the